Pipeline Integrity Management of Landslide Hazards, based on API RP 1187. Techniques to mitigate natural risks impacting pipeline safety. This presentation covers the Pipeline Geohazard Risk Management Framework, from identifying geohazards to assessing, prioritizing, and managing risks, including monitoring, mitigation, and key case studies. Pipeline Geohazard Risk Management is a systematic engineering approach used to identify, assess, and mitigate risks posed by natural and human-induced ground-related hazards that can threaten pipeline integrity. These hazards include landslides, erosion, seismic activity, subsidence, frost heave, and flooding, all of which can impose excessive stress, strain, or displacement on pipeline systems. The objective of geohazard risk management is to reduce the likelihood and consequences of pipeline failure by integrating geotechnical engineering, integrity management, monitoring technologies, and operational decision-making into a unified framework. From an engineering perspective, geohazard risk management emphasizes proactive identification of threats rather than reactive response to failures. This involves understanding the interaction between the pipeline, the surrounding soil or rock mass, and external environmental forces. Pipelines often traverse long distances across varied terrain, making them particularly vulnerable to localized geohazard events that may not be apparent during initial design or construction. Over time, changes in land use, climate patterns, and natural processes can significantly alter ground conditions, increasing risk if not properly managed. Modern pipeline safety regulations and industry standards increasingly require operators to adopt risk-based methodologies. These methodologies prioritize resources toward locations where the combination of hazard likelihood and potential consequences is greatest. API Recommended Practice 1187 provides structured guidance for implementing such an approach specifically focused on geohazards. It aligns geohazard management with broader pipeline integrity management systems, ensuring consistency in terminology, assessment techniques, and documentation. This introductory slide sets the foundation for understanding why geohazard risk management is essential to pipeline safety, regulatory compliance, environmental protection, and public trust. It also establishes the importance of multidisciplinary collaboration among geotechnical engineers, pipeline engineers, operations personnel, and management to effectively manage geohazard risks throughout the pipeline lifecycle. API Recommended Practice 1187, titled Pipeline Geohazard Management, provides industry guidance for identifying, evaluating, monitoring, and mitigating geohazards that may impact onshore pipeline systems. The document was developed in response to increasing recognition that geohazards represent a significant and sometimes underappreciated threat to pipeline integrity. Unlike prescriptive standards, API RP 1187 is risk-based and flexible, allowing operators to tailor their geohazard management programs to specific pipeline systems, environments, and risk profiles. The recommended practice outlines a life cycle approach to geohazard management, integrating activities from route selection and design through construction, operation, and eventual decommissioning. It emphasizes the importance of understanding geohazard mechanisms, such as slope instability or erosion processes, and how these mechanisms interact with pipeline materials and operating conditions. API RP 1187 also stresses the need for continuous improvement through reassessment, data collection, and lessons learned from incidents and near misses. A key feature of API RP 1187 is its alignment with other integrity management standards, including API RP 1160 and regulatory frameworks such as those enforced by PHMSA. This alignment ensures that geohazard risks are not managed in isolation but are considered alongside corrosion, mechanical damage, and operational threats. The standard encourages the use of subject matter experts, documented decision-making, and defensible engineering judgment. For engineering professionals, understanding API RP 1187 is critical not only for compliance but also for implementing best practices that enhance safety and reliability. This slide introduces the purpose, scope, and philosophy of the recommended practice, setting the stage for deeper exploration of its technical and procedural components in subsequent slides. Pipeline geohazards encompass a wide range of ground-related phenomena that can adversely affect pipeline integrity. These hazards are generally categorized based on their underlying mechanisms and the type of ground movement or environmental process involved. Common geohazards include landslides, slope creep, erosion, river scour, flooding, seismic fault movement, liquefaction, subsidence due to mining or groundwater withdrawal, frost heave in cold regions, and expansive or collapsible soils. Each type of geohazard poses unique challenges from an engineering standpoint. For example, landslides can impose large longitudinal and bending strains on pipelines, potentially exceeding material limits. Erosion and scour can lead to loss of cover, increasing vulnerability to mechanical damage or buoyancy effects. Seismic hazards may result in sudden ground displacement, fault rupture, or loss of soil strength, all of which require specialized design and assessment methods. Understanding the type and characteristics of geohazards present along a pipeline corridor is a critical first step in risk management. This understanding is achieved through desktop studies, field investigations, remote sensing, and historical data analysis. Engineers must also consider how multiple geohazards may interact or occur sequentially, such as heavy rainfall triggering both flooding and slope instability. This slide provides an overview of the major categories of pipeline geohazards and highlights why a one-size-fits-all approach is insufficient. Effective management requires hazard-specific assessment techniques, monitoring strategies, and mitigation measures tailored to the physical processes involved and the local environmental context. Geohazard identification is the foundational step in pipeline geohazard risk management, as unidentified hazards cannot be effectively assessed or mitigated. Identification methods combine multiple data sources and investigative techniques to build a comprehensive understanding of ground conditions and potential threats along the pipeline right-of-way. These methods range from high-level screening studies to detailed site-specific investigations. Desktop studies are typically the starting point and include review of geological maps, topographic data, aerial imagery, LiDAR, historical incident records, and climate data. These studies help identify areas with known instability, steep slopes, active faults, or erosion-prone waterways. Field reconnaissance follows, allowing engineers and geologists to visually confirm desktop findings, observe signs of ground movement, and assess drainage and vegetation conditions. Advanced technologies play an increasingly important role in geohazard identification. Remote sensing tools such as NSAR can detect subtle ground deformation over large areas, while UAVs and high-resolution photogrammetry provide detailed terrain models. Geophysical surveys and borehole investigations offer insight into subsurface conditions, soil properties, and groundwater regimes. This slide emphasizes that geohazard identification is not a one-time activity but an ongoing process throughout pipeline operation. Changes in land use, extreme weather events, and aging infrastructure can introduce new hazards or exacerbate existing ones. A robust identification program ensures that emerging risks are recognized early, enabling timely assessment and mitigation. A risk-based approach to geohazard management focuses on prioritizing resources where they will have the greatest impact on safety and reliability. Risk is generally defined as the combination of the likelihood of a geohazard event occurring and the consequences should that event impact the pipeline. API RP 1187 strongly advocates for this approach, as it allows operators to move beyond purely qualitative assessments toward more structured and defensible decision-making. Likelihood assessment involves evaluating factors such as historical frequency of events, current ground conditions, triggering mechanisms, and the effectiveness of existing controls. Consequence assessment considers potential impacts on public safety, the environment, pipeline operations, and company reputation. High-consequence areas, such as densely populated regions or environmentally sensitive zones, warrant particular attention even if hazard likelihood is relatively low. Risk-based frameworks support transparent prioritization, enabling engineers and management to justify inspection, monitoring, or mitigation investments. They also facilitate communication with regulators and stakeholders by clearly explaining why certain locations are addressed before others. Importantly, risk is dynamic and must be periodically reassessed as conditions change or new information becomes available. This slide explains the principles of risk-based geohazard management and highlights its advantages over prescriptive or reactive approaches. It reinforces the idea that effective risk management is iterative, data-driven, and integrated into overall pipeline integrity management systems. Effective geohazard risk management depends on the availability, quality, and accessibility of relevant data. Engineering decisions are only as sound as the information on which they are based. Data requirements span the entire pipeline lifecycle and include geotechnical, geological, environmental, operational, and inspection data. API RP 1187 emphasizes the importance of systematic data collection and management to support consistent and repeatable assessments. Key data types include terrain and elevation models, soil and rock properties, groundwater conditions, historical geohazard events, monitoring results, and pipeline attributes such as material grade, diameter, wall thickness, and operating pressure. Integrating these datasets allows engineers to evaluate how hazards interact with pipeline design and operating conditions. Data gaps or uncertainties should be clearly documented and addressed through targeted investigations or conservative assumptions. Information management systems, such as GIS-based platforms, play a critical role in organizing and visualizing geohazard data. These systems enable spatial analysis, trend identification, and efficient communication across disciplines. They also support traceability and auditability, which are essential for regulatory compliance and continuous improvement. This slide highlights the importance of robust data management practices and explains how high-quality, well-organized data underpins every stage of geohazard risk management, from identification and assessment to monitoring and mitigation. Geohazard susceptibility assessment evaluates how prone a particular location is to specific geohazard processes, independent of pipeline presence. This assessment focuses on natural terrain characteristics such as slope angle, soil type, geological structure, drainage patterns, and climatic influences. The goal is to identify areas where geohazards are more likely to occur so that they can be prioritized for further evaluation. Susceptibility assessments often use qualitative, semi-quantitative, or quantitative methods. Qualitative approaches rely on expert judgment and classification schemes, while quantitative methods may involve statistical modeling or numerical simulations. Regardless of method, transparency and consistency are essential to ensure credible results. API RP 1187 encourages the use of documented criteria and defensible engineering judgment. Importantly, susceptibility does not equate directly to risk. A highly susceptible area may pose limited risk if pipeline exposure or consequences are low, whereas a moderately susceptible area in a high-consequence location may represent a significant risk. Therefore, susceptibility assessments should be viewed as an input to broader risk evaluation rather than a standalone decision tool. This slide explains the purpose and methodology of geohazard susceptibility assessments and clarifies their role within the overall risk management framework. Understanding susceptibility helps engineers focus detailed analyses and monitoring efforts where they are most needed. Pipeline vulnerability and exposure assessment examines how susceptible the pipeline itself is to damage if a geohazard occurs. Vulnerability is influenced by pipeline design, material properties, construction methods, depth of cover, alignment, and operating conditions. Exposure considers whether and how the pipeline intersects with hazardous terrain or processes. For example, a pipeline crossing a steep slope may be exposed to landslide forces, while a shallow buried pipeline near a river may be exposed to erosion and scour. Pipeline material toughness, weld quality, and strain capacity all affect how well the pipeline can tolerate imposed deformations. Older pipelines or those not designed for significant ground movement may be particularly vulnerable. Assessing vulnerability requires close collaboration between geotechnical and pipeline engineers. Analytical tools such as strain-based assessment methods or finite element models may be used to evaluate pipeline response to ground movement scenarios. Field observations and as-built records are also critical inputs. This slide emphasizes that risk is not solely a function of the hazard itself but also of how the pipeline interacts with that hazard. Understanding vulnerability and exposure enables more accurate risk ranking and supports selection of appropriate mitigation and monitoring strategies. Consequence assessment evaluates the potential impacts of a pipeline failure resulting from a geohazard event. These impacts may include harm to people, environmental damage, service disruption, economic loss, and reputational consequences. API RP 1187 stresses the importance of considering consequences alongside likelihood to form a complete picture of risk. Human safety consequences depend on factors such as population density, proximity to occupied structures, and the nature of the transported product. Environmental consequences may be severe in sensitive ecosystems, water bodies, or protected areas. Operational consequences include loss of product, repair costs, downtime, and impacts on supply reliability. Consequence assessment may use qualitative categories, semi-quantitative scoring, or quantitative modeling such as consequence radius calculations. Consistency with other integrity management assessments is important to ensure comparability across threat types. Conservative assumptions are often warranted where uncertainty exists. This slide highlights the role of consequence assessment in prioritizing geohazard risks and ensuring that high-impact scenarios receive appropriate attention, even if their likelihood is relatively low. Risk ranking and prioritization translate geohazard assessments into actionable decisions. By combining likelihood and consequence evaluations, engineers can rank geohazard sites or segments according to relative risk. This process supports efficient allocation of resources for monitoring, mitigation, and further investigation. Risk matrices, scoring systems, or quantitative risk metrics may be used, depending on the maturity of the program and data availability. Transparency in scoring criteria and weighting factors is essential to maintain credibility and support internal and external communication. API RP 1187 encourages documentation of assumptions and rationale behind risk rankings. Prioritization is not static. As new data become available, mitigation measures are implemented, or conditions change, risk rankings should be updated. This dynamic process supports continuous improvement and adaptive management. This slide explains how risk ranking bridges the gap between assessment and action, ensuring that geohazard management efforts are focused on the most significant threats to pipeline integrity and safety. Monitoring is a critical component of geohazard risk management, providing early warning of changing conditions and validating assessment assumptions. Effective monitoring strategies are tailored to the type of geohazard, risk level, and site-specific conditions. They may include periodic inspections, continuous instrumentation, or remote sensing technologies. Common monitoring methods include slope inclinometers, extensometers, piezometers, strain gauges, GPS surveys, NSAR, and visual patrols. The selection of monitoring tools should consider reliability, data resolution, maintenance requirements, and response time. Trigger thresholds should be established to define when further investigation or mitigation is required. Monitoring data must be systematically reviewed and integrated into decision-making processes. Simply collecting data is insufficient without clear procedures for interpretation and response. API RP 1187 emphasizes the importance of defining roles, responsibilities, and escalation protocols. This slide underscores how monitoring supports proactive risk management by detecting early signs of instability, reducing uncertainty, and enabling timely intervention before pipeline integrity is compromised. Inspection and surveillance programs complement monitoring by providing direct observation of pipeline and right-of-way conditions. These programs help identify surface expressions of geohazards, such as cracks, scarps, erosion gullies, or exposed pipe. Regular inspections are especially important in areas with known or emerging geohazard risks. Inspection methods may include ground patrols, aerial surveys, UAV inspections, and targeted field investigations. Frequency and scope should be risk-based, with higher-risk areas receiving more frequent and detailed attention. Inspectors should be trained to recognize geohazard indicators and document findings consistently. Surveillance programs also play a role in detecting third-party activities, land use changes, or drainage modifications that could increase geohazard risk. Integration of inspection findings with GIS and integrity management systems enhances data value and traceability. This slide highlights the importance of structured inspection and surveillance programs as part of a comprehensive geohazard management strategy, reinforcing the need for vigilance and timely reporting. Mitigation measures are implemented to reduce either the likelihood of geohazard occurrence or the severity of its impact on the pipeline. These measures can be preventive, corrective, or adaptive, depending on the nature of the hazard and risk level. API RP 1187 encourages selection of mitigation options based on engineering effectiveness, feasibility, and risk reduction potential. Common mitigation strategies include slope stabilization, drainage improvements, erosion control, river training works, increased depth of cover, mechanical protection, pipeline rerouting, and operational control such as pressure reduction. In some cases, enhancing pipeline strain capacity or installing flexibility features may be appropriate. Mitigation design should be informed by site-specific investigations and analysis. Poorly designed or implemented mitigation can inadvertently increase risk or create new hazards. Therefore, quality assurance, constructability review, and post-installation verification are essential. This slide provides an overview of mitigation concepts and sets the stage for more detailed discussion of specific mitigation approaches in subsequent slides. Slope stability mitigation techniques aim to reduce the likelihood or magnitude of landslides and slope movements that could impact pipelines. These techniques address the underlying causes of instability, such as excessive driving forces or insufficient resisting forces within the slope. Common approaches include regrading slopes to reduce steepness, installing retaining structures, improving drainage to lower groundwater levels, and reinforcing soil or rock masses with anchors, piles, or geosynthetics. Surface erosion control measures, such as vegetation or erosion mats, may also contribute to long-term stability. Selection of appropriate techniques depends on slope geometry, material properties, groundwater conditions, and environmental constraints. Engineering analysis, such as limit equilibrium or numerical modeling, is often required to demonstrate effectiveness. Long-term performance and maintenance requirements should be considered. This slide explains how slope stability mitigation reduces geohazard risk and highlights the importance of sound geotechnical design and monitoring to ensure sustained performance. Erosion and scour are significant geohazards for pipelines crossing rivers, streams, or areas with concentrated surface runoff. These processes can remove supporting soil, reduce cover, and expose pipelines to mechanical damage or buoyancy forces. Effective erosion and scour protection is therefore critical to maintaining pipeline integrity. Mitigation measures may include rock armoring, concrete mats, geotextiles, grade control structures, bank stabilization, and channel realignment. The design of these measures must account for hydraulic conditions, sediment transport, and extreme flow events. Climate change and increased storm intensity should also be considered. Regular inspection and maintenance are essential, as erosion protection measures can degrade or be displaced over time. Adaptive management may be required if river morphology or flow patterns change. This slide discusses common erosion and scour protection strategies and emphasizes the need for integrated hydraulic and geotechnical engineering to manage these dynamic hazards effectively. Seismic hazards pose unique challenges for pipeline systems, particularly where pipelines cross active faults or traverse seismically active regions. Earthquake-induced ground shaking, fault displacement, liquefaction, and lateral spreading can impose significant demands on pipelines. Engineering considerations include route selection to avoid active faults where feasible, design for flexibility and strain capacity, and implementation of specialized fault crossing designs. These may involve thicker wall pipe, reduced operating stress, or engineered transition zones. Seismic risk assessment requires integration of regional seismic hazard data, site-specific geotechnical investigations, and pipeline response analysis. Emergency response planning is also a critical component of seismic risk management. This slide outlines key seismic considerations and highlights how proactive design and assessment can reduce the risk of catastrophic pipeline failure during seismic events. Operational controls are non-structural measures used to reduce geohazard risk by limiting pipeline exposure or consequence. These controls may include pressure restrictions, flow rate limitations, seasonal operating adjustments, or enhanced surveillance during high-risk periods. Operational measures are often implemented as interim controls while longer-term mitigation is designed or constructed. They can be highly effective when integrated with monitoring data and clear decision criteria. However, reliance solely on operational controls may not be sustainable over the long term. Clear documentation, training, and communication are essential to ensure operational controls are implemented consistently and effectively. Integration with control room procedures and emergency response plans enhances overall risk management. This slide explains how operational controls fit into a layered defense strategy, complementing engineering and monitoring measures to reduce geohazard risk. Emergency preparedness and response planning is a vital component of geohazard risk management. Despite best efforts, some geohazard events may still occur, and the ability to respond quickly and effectively can significantly reduce consequences. Plans should address scenarios such as landslide-induced rupture, river crossing failure, or seismic damage. Key elements include communication protocols, shutdown procedures, access planning, and coordination with emergency services. Training and drills help ensure readiness. Monitoring and inspection data can provide early warning that enables preemptive action, such as pressure reduction or shutdown. Lessons learned from incidents and exercises should be incorporated into continuous improvement efforts. This slide emphasizes that preparedness is an integral part of risk management, ensuring resilience when prevention and mitigation measures are exceeded. Documentation and record-keeping underpin credible and defensible geohazard risk management programs. API-RP 1187 emphasizes the importance of maintaining clear records of assessments, decisions, monitoring data, mitigation designs, and inspections. Well-organized documentation supports regulatory compliance, internal audits, and knowledge transfer. It also enables traceability, allowing engineers to understand why certain decisions were made and how risks were prioritized. Records should be stored in accessible systems and updated as conditions change. Consistent terminology and standardized formats enhance usability across disciplines. This slide highlights the role of documentation in supporting transparency, accountability, and continuous improvement in geohazard management. Clear definition of roles and responsibilities is essential for effective geohazard risk management. Multiple disciplines and organizational levels are involved, including geotechnical engineers, pipeline engineers, operations staff, integrity management teams, and management. API-RP 1187 encourages assignment of accountability for key activities such as hazard identification, assessment, monitoring, and response. Interfaces between teams should be clearly defined to avoid gaps or duplication. Competency and training requirements should be established to ensure personnel are qualified to perform assigned tasks. Leadership support is critical to provide resources and reinforce the importance of geohazard management. This slide explains how clear roles and responsibilities contribute to program effectiveness and organizational alignment. Competency and training are fundamental to the success of a geohazard risk management program. Personnel involved in identifying, assessing, and managing geohazards must possess appropriate education, experience, and skills. Training programs should cover geohazard mechanisms, inspection techniques, data interpretation, and emergency response procedures. Continuing education helps personnel stay current with evolving technologies and best practices. API-RP 1187 emphasizes the use of subject matter experts for complex assessments and encourages documentation of competency requirements. This slide highlights the importance of investing in people to ensure that technical and procedural elements of geohazard management are effectively implemented. Geohazard risk management should be fully integrated with broader pipeline integrity management systems. This integration ensures consistency in risk assessment, prioritization, and decision-making across all threat types. Data sharing, aligned risk criteria, and coordinated planning enhance efficiency and avoid siloed approaches. Integration also supports holistic understanding of pipeline risk and cumulative impacts. API-RP 1187 aligns with other standards to facilitate this integration. This slide explains the benefits of integrated integrity management and how geohazards fit within the overall risk framework. Change management is essential in geohazard risk management because conditions affecting risk are constantly evolving. Changes may include new development, climate impacts, operational modifications, or updated regulatory requirements. Formal change management processes help ensure that geohazard risks are reassessed when significant changes occur. Periodic reassessment is also necessary even in the absence of obvious changes. API-RP 1187 encourages proactive reassessment to maintain program effectiveness. This slide highlights the importance of adaptability and vigilance in managing dynamic geohazard risks. Performance metrics and key performance indicators (KPIs) are used to evaluate the effectiveness of geohazard risk management programs. Metrics may include number of identified hazards, inspection coverage, mitigation completion rates, or incident trends. Well-defined KPIs support continuous improvement and management oversight. They also facilitate benchmarking and reporting. API-RP 1187 encourages use of meaningful metrics aligned with program objectives. This slide explains how performance measurement supports accountability and program maturity. Regulatory bodies increasingly expect pipeline operators to address geohazard risks systematically. Compliance with API-RP 1187 demonstrates alignment with recognized industry practices. Regulators may review documentation, risk assessments, and mitigation actions. Clear demonstration of risk-based decision-making is critical. This slide highlights regulatory drivers and the importance of defensible geohazard management programs. Historical pipeline incidents provide valuable lessons for improving geohazard risk management. Many failures have been linked to inadequate identification, monitoring, or response to geohazards. Systematic analysis of incidents and near misses helps identify program gaps and improvement opportunities. Sharing lessons learned across organizations enhances industry safety. API-RP 1187 encourages incorporation of lessons learned into continuous improvement. This slide underscores the importance of learning from past events to prevent future failures. Advances in technology are transforming geohazard risk management. Remote sensing, advanced monitoring systems, data analytics, and machine learning offer new capabilities for early detection and risk assessment. Adoption of innovative tools should be guided by clear objectives and validation of performance. Technology complements but does not replace sound engineering judgment. This slide highlights emerging technologies and their potential benefits for geohazard management. Effective communication with stakeholders is essential in managing geohazard risks. Stakeholders may include regulators, landowners, communities, and internal management. Clear communication builds trust and facilitates cooperation during mitigation and emergency response. Technical information should be conveyed in an understandable manner. This slide emphasizes the role of communication in successful geohazard risk management. Auditing and periodic review help ensure geohazard risk management programs remain effective and aligned with best practices. Audits may be internal or external and should assess both processes and outcomes. Findings should be documented and addressed through corrective actions. Reviews support continuous improvement and accountability. This slide highlights the value of auditing in maintaining program quality. Continuous improvement is a core principle of API-RP 1187 and effective geohazard risk management. Programs should evolve based on new data, technology, and experience. Feedback loops, performance metrics, and lessons learned drive improvement. Management commitment is essential to sustain progress. This slide reinforces the importance of viewing geohazard management as an ongoing process rather than a one-time effort. A case study of a landslide-affected pipeline illustrates practical application of geohazard risk management principles. The scenario involves identification of slope movement, assessment of pipeline strain, and implementation of mitigation measures. Key lessons include the value of early detection, interdisciplinary collaboration, and adaptive management. Monitoring played a critical role in guiding decisions. This slide demonstrates how theory translates into practice. This case study examines a pipeline river crossing impacted by scour. Inspection identified loss of cover, prompting detailed hydraulic analysis and mitigation. Rock armoring and monitoring were implemented, reducing risk. The case highlights importance of inspection and timely response. This slide reinforces key concepts through real-world example. Common challenges in geohazard risk management include data gaps, underestimation of risk, inadequate monitoring, and organizational silos. Over-reliance on qualitative judgment without documentation can undermine credibility. Addressing these challenges requires robust processes, training, and management support. This slide discusses pitfalls and strategies to avoid them. Future trends include increased use of remote sensing, real-time monitoring, and data analytics. Climate change considerations will play a larger role in hazard assessment. Regulatory expectations are likely to evolve, emphasizing proactive risk management. This slide looks ahead to emerging trends shaping the field. This concluding slide summarizes key takeaways from the presentation. Effective pipeline geohazard risk management is risk-based, data-driven, and integrated across disciplines. API-RP 1187 provides a structured framework to identify, assess, monitor, and mitigate geohazards throughout the pipeline lifecycle. Continuous improvement, competency, and communication are essential to success. The presentation reinforces the importance of proactive management to protect people, the environment, and pipeline assets.